this spectroscopic identification? Well, if anything, this is probably the most important concept. Okay, this is actually 11.3, not 1.3. I don't know what I was thinking. Okay, so we're actually back to chapter 11. So remember, chapter 11 is about significant digits. It was about uncertainty. Remember that back in September when I barely know any of you, and I hope I do know all of you. Okay, I do hope that I know everyone by name, by their name by now. But you'll be surprised. Anyway, 11.2 was about graphing. So 11.3 we didn't do. That's because we can't do until we learn about organic nomenclature and organic reactions. So here we are, the very last section of this course, 11.3, spectroscopic identification. Now, what is this all about? Well, if somebody were to give you an unknown organic chemical, how do you know what it is? Now, we've sort of done something like this before. Okay, we talked about gas chromatography and mass spectrometry when we were talking about empirical and molecular formula. Now, it's sort of the same kind of thing, but more graphically, or more graphical, more analysis and stuff like that. So let's take a look at the 4 ways, okay, we can identify organic molecules by mean of experimentation or by mean of mathematical determination. So the first one is called IDH, Index of Hydrogen Deficiency. Now, you probably have already know that when you have an alkene or a cycloalkane or an alkyne, you have less hydrogen. So hence hydrogen deficiency. Now, this is of course based on numbers. Okay? It's a numerical method of determining what kind of bond your unknown might have. So this is how you would determine these kind of things. There's a set of things that you have to know, like double bond, a carbon-carbon double bond, or any double bond actually. It's given the value 1. So it really doesn't have to be carbon-carbon double bond. It could be carbon-oxygen double bond. Okay, so it gives a value of 1. Carbon-carbon triple bond has a value of 2. Any cyclic structure like cyclohexane, cyclopentane, cyclobutane, cyclooctane, they're all given a value of 1. Benzene, if you remember that, okay, the aromatic molecule looking like this has an IDH value of 4. Okay, so try to, I guess, memorize that. Okay, so, double bond is 1, triple bond is 2, cyclic is 1, benzene is 4. Now, the IDH can be worked out in 2 ways. 1, from the structure of the compound. By looking at the structure of the compound, we can determine its IDH value, or total IDH value. Or from the molecular formula itself. Now, we're going to look at both ways and take a look at how the determination came about. So let's do some examples. Hey, let's try out our nomenclature skills. So here it is. IDH. Let's take a look at example 1. Example 1 is cyclopentadiene. So if you were to draw cyclopentadiene, okay, it really doesn't matter. They just want to know a cyclopentadiene. That's an example of a cyclopentadiene. I know this is not specific enough because they should have said, in this case, 1,3 cyclopentadiene, but that's not the point. The point here is, what is the IDH value for this particular molecule? Well, it's pretty simple. Okay, there's a double bond here, a double bond here, and a ring. Okay, Having said all that, this is 1. This is 1. The ring itself is 1. So cyclopentadiene has an IDH of 3. Okay? Now, a couple of more down here for you to do. So what about this guy over here? Okay, I wouldn't try to name him Upackley, but what we do know is that this is aspirin. Okay. Hey, why don't you start counting and find out? All right. Hopefully you count it right. So what you have here is a benzene that is worth 4. A couple of double bond here that worth 1. So the answer to this, of course, will be 6. All right. So aspirin has an IDH of 6. Ethine. Okay. We'll have an IDH of course, we see here a carbon-carbon triple bond. That's worth 2 and nothing else. So the IDH value here, of course, is 2. Okay. Now, would you say IDH is very useful in terms of identifying an unknown? I would say no, at least not by itself. And we'll see by the end of this section when it can be useful. I can tell you right now that it is very useful later on when you're checking to see if you got the right structure. Okay, but of course you need to know how to identify the IDH number for these guys. All right, let's continue. So what about from molecular formula? Okay, if I have an example right here, C4H8O2, what is the IDH number for this? Now you may be thinking, well, do I have to draw this? Because if you're going to ask me to draw this, my goodness, I have lots of isomers for you. No, you're not going to be asked to draw this. But what you are going to be asked to do is find the IDH for this, given this formula right here. Okay? Now, these C's, H, X, and N is based on the number of carbons, number of hydrogen, number of halogens, and number of nitrogen. All right? So, let's take a look at some of these guys right here. So, C4H8O2. So, if you were to take 0.5 and you multiply that by 2 times, well, what is the number of carbon? Well, it's 4. So, you put that in, 4 plus 2 minus H. So you look at how many H's. Well, there are 8 H's. Minus X. Well, there's no halogens here, aren't they? So you put a 0 down, and you just put nothing down. Plus N. Well, N means nitrogen. There's no nitrogen here as well. So therefore, that's another 0. All right, so sum that all up. That will equal to 1. Okay, hopefully my mathematical skills hasn't deteriorated yet, but that's the IDH for this compound right here. So what does that say? Oh, C4H8O2 has an IDH of 1. What does that mean? Well, that means a couple of things. Okay, means C4H8O2 has maybe a double bond. Okay, let me just write that down nicely. Has, I don't know, double bond. Okay. Maybe a cyclic. Okay, so both double bond or cyclic has an IDH of 1. Okay, we got it from here. right here. So C4H8O2. This unknown will have a, well, may be cyclic. It may have one double bond. So, hey, who knows? As I said, there has to be more proving for you to know what these compounds really are. All right, why don't you guys do this one? Okay. Pause and unpause. All right, so, oh, by the way, before we continue, do you know what this is? No, I didn't make this up, by the way. I did not make this up. This is a legit compound, C17H21NO4. I wouldn't try to name this iupacly, but I know the street name for this. That's right, this is cocaine. Yikes. I have no idea what that is. Okay, I have no idea what that is. All right, so let's apply the formula. So 2 times 17 plus 2 minus 21 minus 0 plus 1. Okay, and putting all that together, you should have, let's see, 8. Okay, so cocaine has a IHD of 8, which means, hey, this 8 could be 8 double bond. I don't know. Maybe 7 double bond in one ring. Maybe a triple bond, 7 double bond. Who knows? 1 triple bond, 6 double bond. No, not that. Yeah. Who knows? Okay. All we know is that the IDH of this chemical formula is 8. Okay, so it's a very interesting molecule. Okay, hey, you know what? Maybe you guys can look this up on the internet and start counting like you did right here. Okay. All right. Let's do one more. So you may pause, I guess, and come back and see if you got the right answer. All right. While you unpause, I have worked this out, okay, to be 5. Okay. Now this is also very special. This is again not something that that I made up. Okay. This is not another drug. No worries. Okay. This is actually something could be good for you, could be bad for you. Okay. It's cholesterol. This is cholesterol. So it's a steroid. Okay, there are good cholesterol and there are bad cholesterol. Well, hey, this is one of the many kinds of cholesterol. Okay, so and it has an IDH of 5. So that could mean, hey, maybe it has 5 rings. Maybe it has 4 rings and 1 double bond. Maybe 3 rings and a triple bond. Who knows? Okay, maybe you guys can find a picture of cholesterol and start counting. Okay, hope it gives you a IDH of 5 kind of thing. All right, so that's IDH. IDH, very important, and it is a good way later on to check to see if we have the right molecule, because we're going to talk about the second method of spectroscopic identification, and that's using the technology of infrared. Now, this is an IE spectrometer. It is usually hooked up to a computer because it needs to graph out the data that it collects. Now the question is, what does this do? Do we have one at Millikan? I can tell you we don't have one of these at Millikan. Okay, why? Can't afford it because it's expensive. Well, what does it do? Okay. Well, what it does is something very, very cool. Is that if you were to put, let's say you have an unknown solution, okay, it's an organic solution, and you put it into a little vial. Okay, you open this lid right here and you put it in there, press enter, and it will analyze the functional group of this unknown compound for you. Pretty cool, huh? So if it's a carboxyl, it will start graphing what a carboxyl look like. If it's an aldehyde, it will start graphing what an aldehyde look like. It's a very, very cool machine. Hopefully one day you have the experience of running one of these things, and I'm sure you will if you're going to be asked to study organic chemistry later on, or pharmaceutical chemistry later on, and that is obviously something you will encounter. So here it is, the infrared spectroscopy. So what does infrared do? Infrared, we all know, is not harmful at all. It is a very weak radiation, but okay, when you release it to a molecule, it tends to vibrate and deform bonds temporarily. Okay, now I'm going to use oxygen as an example. Okay, oxygen. I'm going to use water as an example. We all know, okay, that of course this is the structure of water. Okay, it has a stretch that is symmetric. Okay, this is called a symmetric stretch. Okay, dealing with, of course, dipole moments. Wait, hold on. What am I saying? The arrow should go this way. There you go. Okay, this is called symmetric stretch. Why a symmetric stretch is because if this is the symmetry line or dividing line, both of these vector is sort of opposite from each other, or symmetrical from each other. Okay, now once you kind of shot IR into this molecule, these dipole moment will start to deform or start to change. Maybe at a certain instantaneous point, it becomes asymmetrical. So we call this asymmetric stretch. So what does an asymmetric stretch look like? I don't know, maybe one of the dipole is going this way, which is normal, and the other dipole is going at the abnormal situation. So if you were to put a dividing line here to look at the symmetry, you can see that the symmetry here are not the same. So that's why we call this asymmetrical stretch. This is temporarily. Okay, very soon, after when the infrared is gone, it will come back over here like that. But that's what infrared have the ability to do. Now, sometimes it may even do something as strange as this. Okay, where oxygen pulled down this way and hydrogen decided to pull downwards this way. That can happen too. And this is called a symmetric bend. Okay, so when you shot IR onto an organic compound to analyze what it is, all three of these things can happen simultaneously to your organic molecule. Now, that's just really the theory behind the infrared spectroscopy. How do we read an infrared sheet? Okay, as I said, this type of spectroscopy helps us identify the functional group of an unknown compound. Now, it takes a lot of experience to get really, really good at this. So don't go too hard on yourself if you don't understand it the first time, or you're having a hard time trying to understand it, because it really you need to be in the organic industry in order to be really good at identifying these graphs. So let's go. This is an infrared spectroscopy graph. It is a graph on butanoic acid. Oof. Let's draw that. This is butanoic acid. It's a 4-carbon carboxylic acid. And if you were to put this compound into this chamber, this graph will be shown on your computer. This graph is based on transmission, percent transmission. Okay, so what you're looking at is how much infrared light has gone through versus wave number, okay, per centimeter. Now, this is not important for you right now. You're not being asked to explain how this works, how the relationship of this works. Your job is to be able to look at this and say, okay, I can see carboxyl. Wow. How did I do that, right? Don't worry. Okay, don't worry. Let's take a look at this. Now, this is from your IB booklet. Okay, it is page or topic 26, so page 26. It shows different functional group. Okay, and it's wave number, how should I say this? Wave number, I don't know. Okay, it's wave numbers. And how strong they are, how broad they are. Okay, now what do you mean by strong? Strong means, now this is strong. Okay, you see how the graph actually dips? What do you mean by broad? Broad means thick, like this. This is broad. So in this case, this is broad and strong. This is just strong. Okay, this will be weak. And it's not broad at all. So that's what it is. That's why we call this intensity. Okay, so let's look at the butanoic acid again. Okay, let me draw butanoic acid again, so you kind of know and you can check out exactly what we're talking about here. So here's butanoic acid. Okay, and I have already identified a couple of things here for you. Let me just circle them. So I have this and this that I'm going to worry about. Okay, so what this is this. Yeah, what this is this. From here to right about here. Okay, this will indicate what your functional group is. Okay, so if you're wondering, what is the functional group in this graph? What is it indicating? Is it indicating the carboxyl that I'm looking at? Well, you check out this region. Okay, now everything else below that is based on what we call fingerprint region. So you can even say others. Okay, no functional group, just maybe an alkyl and everything else, maybe even noise. Right? So your main goal when looking at these graphs is this region. This is the more important region. So everything here you would say is important, and everything else here you can kind of ignore. All right, so let's take a look at butanoic acid. There's two places which I'm very interested in, and let me circle that right now. Circle that with pink. I'm interested in this, and I'm interested in this. Okay, now this right here, sort of peaked at 3000, like I said. Okay, this 3000 is pretty strong, pretty broad. So let's go back and look at this. So remember what we said, 3000, around 3000, look at these ranges. 3000, very broad and strong. Okay. I guess this matches. Okay, this certainly matches with what we were talking about. It does hit the 3000 range. It is very strong and very broad. Oh, look. Huh. It's a carboxyl. Okay. So, is this a carboxyl? Absolutely, this is a carboxyl. There's the carboxyl. So whenever there is a carboxyl, whenever there is a C double bond OOH, COOH, no matter what molecule you're looking at, it could be methanoic acid, ethanoic acid, propanoic acid, they're all going to give you this similar peak. Okay? Now, there's a secondary peak that kind of proved this, and that's this one right here. Okay? And I kind of looked at this one and say this is probably around in the 1750 mark. It is strong, but not broad. So I go back here and look to see if that matches with any of the description. And guess what? Yes, I do. It's around here somewhere within this kind of range. It is strong, not broad. Hey, again, proved it to me that this is the C double bond O part of a carboxyl. Okay? So, again, let me just clear this up a little bit here. Oh, that's a bad idea. Okay, here it is. Okay, so what these peak are showing is that this peak right here is actually talking about this guy. Okay, this peak right here is actually talking about this guy. And for every carboxyl, you will see both of these. Because every carboxyl will have an OH, and every carboxyl will have a C double bond O. Now, what if it's just an OH without this? Would I still have this, but without this? Well, check it out. Okay? It actually doesn't. If you're looking at just an alcohol, you will be looking at a strong broad as something a lot later. So let's say, okay, you're looking at this guy. Just this guy. Okay, ethanol. You'll notice that it won't have this because this is talking about C double bond O. It will have this because it's an OH, but this will be adjusted more towards maybe like here instead. Okay? I know, seeing this for the first time, it can be quite confusing, but as I said, the only way to get good at this is to see this for months and years. So all you need to do is to be able to interpret that, oh, I see, I know how to use this chart, okay? I know how to communicate that chart with this graph, and I see where these guys are talking about carboxyl. Oh yeah, I know now. But of course, as an expert in infrared spectroscopy, you would be able to interpret what these guys are too. In fact, well, right now, I think these things give me a headache, so let's not look at them right now. Okay? All right. How about you guys try this one? This is, there you go. Okay. See if you're able to identify what this thing is. I'm going to tell you that the molecular formula is C2H6O. The thing is, what molecule is this? Because if you were to draw this out, this thing could be CH3, CH2OH. Okay, it could be ethanol. But it can also be CH3O, CH3. Okay, that will be diethyl ether. So, what would it be by looking at this graph? Would it be alcohol or would it be an ether? So, why don't you look at the chart and tell me after you unpause? All right, after you unpause, I'm sure you guys have an answer for me, right? So we kind of mentioned this before. We actually we did. This is actually ethanol. It's actually this guy right here. This is the right answer. Okay, how do we know? Well, remember, from here to here, it tells you the functional group. Okay? Everything here we can just ignore. Please ignore. But of course, what we're working with right here is this peak and this peak. Okay? This peak is around 3358. So if you go back to this chart and you look at, okay, 3358. Looks like somewhere here. Oh, and it's strong and broad. That's pretty strong and broad. Ah, it's an alcohol. Do I see ether? No, I don't see ether. So therefore, it must be this one. Okay. All right. Hey, what about this? What is this? Okay, 2974. This has to mean something, right? Well, it does. It does mean something, but it's not something that important. Okay, this is just an alkane. Just showing you that, yeah, there's alkane in here. Yeah, no kidding, there's alkane in here. What are these, huh? Okay. So if you go back here, how come it didn't have that? Well, it did. It was this. It was hiding behind the OH of carboxyl. It is there. Okay, but it's kind of blended because remember the OH of carboxyl sort of overlap all of this. All right. I hope that's what you guys got. So what would this look like? What would an ether look like? Well, hopefully they have something here about ether, because I'm not sure they have everything. They have esters. Oh yeah, there's ether. Okay, the CO bond of ether, you'll have a very strong peak at 1050 to 1410. So that would be around here. Okay, around here you'll see something like this. If it was, sorry, 1410, yeah, right here. Okay, it'll be here, strong and broad, if it was this guy. Because that's what it says. Okay, an ether will have a very strong peak at around that area. Anyway, I hope you got the right answer, and I hope you guys are comfortable with IDH and IR. So tomorrow, Monday, okay, this time for real now, we will talk about HNMR, and we'll talk about the whole idea of mass spectrometry. I know we just talked about how it gives you the molar mass of an unknown, well, I'm going to show you exactly how it gives you its molar mass and what exactly is mass spectrometer does. Okay, all right, so we'll leave it here. Hopefully you're comfortable with IHD and IR. If not, you can rewatch this video again or just ask me any question you want. Okay, don't forget to do those mechanism questions or those pathway questions. I don't know why I keep calling it mechanism questions, because they're not. Do those pathway questions. There's 5 of them. I hope you can do them all. All right, and I'll see you on Monday. Bye.